So, hi everyone. Welcome to our first research discussion on our channel, Research Charcha, and myself Suman. And today we are joined with Dr. Abhay Sagade from SRM University. And hi Abhay here.
Hello, hi Suman.
And thank you for joining us in our channel Research Charcha. And let me first discuss about his professional achievement of Dr. Abhay. So he is currently working as an associate professor at Department of Physics and Nanotechnology, SRM Institute of Science and Technology. And he received his PhD degree from Dr. Babasaheb Ambedkar Marathwade University, India on 2009. And after that, he did several postdocs from various institutes, including JNCSR Bangalore, AMO Germany, as well as University of Cambridge, UK. And he has been authored in more than 40 publications till now. And recently, one of his work titled that 100 gigahertz Schottky diodes processed from solution on a wafer scale has been published in the prestigious journal Nature Electronics. And today we will be discussing on that work. So what do you, Abhay?
Yes, thank you, Suman. This is fantastic idea when you pitched to me that we don't have a channel on YouTube which discusses about the new researchers and for the researchers. So good luck for that. Hope you will have a lot of viewers and you will get interesting speakers.
Yeah.
Okay. So I will start sharing my screen now.
Yes.
Yeah. So the title of my research presentation here today is on device scaling for novel materials in high frequency nonlinear electronics applications. So please feel free to visit my homepage and contact me if you have any new research ideas and if you want to collaborate. I'm always looking for the interesting people to join us. So currently my research work is focused on making new device designs and making electronic applications out of it. So it may be two-dimensional materials like graphene or MOS2. And basically I'm much more interested in making use of existing materials rather than their material synthesis. As you can see, the applications are in RF transistors or flexible chips, then digital logics, then Hall sensors, organic nanowire transistors, or memory applications, or even some moisture barriers as well. So today I want to share with you a special topic in it called RF electronics. So when we talk about devices, electronic devices, we know that there is something called Moore's law, which is related to transistor, field effect transistors design. And over the years, the size of transistor is decreasing in an integrated circuit. So when we talk about that scaling, then few parameters comes into the picture. First one is a quantization of both electrical and thermal conductance in a narrow channels. Then spread of doping atom in a semiconductor, because as the size decreases, you will have a very small region where the doping atoms are present and they may get spread over a small distance. Then electrostatics, like how much is the control of gate current from sorry, drain current from gate voltage. Then electron tunneling, because of now the small narrow regions, there may be possibility of tunneling of electron. So what we generally don't pay attention to is the propagation of electromagnetic waves across the chip. So now if we are talking about uh, measurement of electronic devices based at various frequencies, and this is because from last a decade or so, there is an explosion of wireless connectivity. So like whether we are being on a road, in a vehicle, or in a walking, or either we are in a aeroplane, we are always connected with a wireless network. So we use those networks for communication, of course, and that is what where this electromagnetic wave interaction with the chips comes into the picture. So we use rate of data change from 100 Mbps to 1 Gbps, and we use it for industrial applications and domestics and security. So why this happened is because of the invention of new cellular phones, like the phones which has internet functionality in it. Then next one is satellite communication, means we have now direct to home satellite at our to just see TV and internet. Then next two terms are technical ones. They are called as wireless local area network, WLAN, or WPAN, which we know famously as a Bluetooth. So let's look at what is the physics behind these RF devices. So when the when we pass electrical current to a conducting metal, let's say like a copper, then as if this wire diameter is like circular like this, then electron is completely filled, or the motion is completely filled inside the wire. So this is a cross section of a wire, and the whole orange color shows the filling of electron. But now if you increase now the frequency of that signal, then you will see the electrons are not conducting over inside the bulk, but they start coming closer to its surface. And now if you increase that frequency little bit higher, then the electron current is only restricted to the surface region of the nanowire. And in physics terms, this is called as a skein effect. So at higher frequencies, the DC resistance and AC resistance can be defined separately, and they have different values. Now let's look at the electromagnetic spectrum. So this is electromagnetic spectrum starting from high wavelength, and then the wavelength goes down or the frequency goes up. So here is a microwave, then IR, visible, UV, X-rays, and gamma rays. What we are going to discuss today is about this microwave frequency. So this frequency, it interacts with the material in various ways. Very specifically, these radiations do not cause any ionization, unlike IR, visible, UV, X-rays, gamma rays. They cause some kind of a ionization in the material. But this frequency range of microwave creates some thermal effects in the material, and you can understand this is because of this skin effect and this phenomena which we just discussed. So now if we measure the skin depth, how much is the skin depth? So this region here in this orange region, how much is the skin depth for well-known materials like titanium, aluminum, copper, stainless steel. As with increase in frequency, you can see it fairly straight line and it decreases continuously. And it can be obtained using this formula where rho is a frequency, omega rho is a resistivity or conductivity, omega is the frequency, and mu is the permeability of that material. So when we are talking about now RF devices, of course we are talking about the devices which are operating at high speed. Then the basic backbone of those, if RF systems or RF circuits are as usual diodes and transistors. So now we have to define figure of merits of for those devices. So these are known as cutoff frequency, then noise figure, and how much is the output power. So we will talk about or we will see these parameters in more detail in few minutes. So basically, as we know, the Moore's law as scaling is progressing, and the limit has been reached a few years ago. And these and from last almost 4 or 5 years, researchers are talking about going more than more. So that's why there have been a new concepts coming in called the 3D integration. So on which chip on chip is developed, or chip on wafer or wafer on wafer technology is getting more attention and successes in last couple of years. So likewise, in this direction, you can see the dimensions of the device is decreasing, and people are using it for CPU or logic applications. And then this is the another way on which people talk about RF applications, passives, sensors, and towards biomedical applications. So when we talk about electronic devices, we know there are passive and active components in circuits. So diodes and transistors are active components. So specifically here transistor is a field effect transistor, and diodes are Schottky and PIN. So PIN is a P-type and N-type semiconductor separated by an insulating region. And these diodes and transistors are used to make RF circuits like transmitters and receivers, filters, oscillators, mixers, switches, detectors, and converters. All of these are required for this communication. So now when we are coming to the figure of merits of diode, then channel length means how much is the separation between the two metals or the width of a semiconductor, then how much voltage is applied to it, then its thickness, then how much is the loss of that wave which is coming into it at higher frequencies like 10 gigahertz, then what is its series resistance, junction resistance, and capacitance, input power, and corresponding to that, how much is the DC output voltage generated. So here everything is about making a junctions between metal, semiconductor, and insulator. So when we talk about metal and semiconductor junction, then it can be of ohmic or Schottky type. So these are the energy band diagrams which represents what it means ohmic and Schottky junction. So today we are going to see specifically about high frequency diodes. So in general, we know the diode is fabricated between semiconductor. One is a p-type semiconductor and other one is an n-type semiconductor. But if we make a diode between a metal and semiconductor, then it is called as a Schottky junction, Schottky barrier diode. So this is achieved by selecting one metal with a work function larger and other metal which has a work function smaller than the work function of semiconductor. So this review explains this Schottky barrier fantastically, and this is almost a decade older review. So if you look at now the DC IV characteristics, current voltage characteristics of these two diodes, then this red one is for a PN junction diode and this blue line is for a Schottky diode. So this is a forward bias and this is a reverse bias region. So if you look at this very specifically in this small region where this PN junction diode still has very low current or it is below threshold voltage, then if we compare what is the IV of Schottky diode, you can see that by the time PN junction diode gets turned on, Schottky diode already has a very high current. Of course, in the reverse direction also, the currents are a little bit larger. But here the point is how quickly we can switch the divides. So this is one graph which tells how quickly the currents in these two diodes switched from forward current means high current to reverse current means low currents. So this blue, red line is for a PN junction. Sorry, this red line is for a Schottky and blue line is for a PN junction. And TRR is the time which is taken by this current to switch back to more than 50%. So you can see Schottky diodes are switching at a time of nanoseconds, while PN junction diode takes microseconds. Means PN junction diodes are 1000 times slower than Schottky diodes. And this is the key of using Schottky diodes in high frequency applications. So why this study was important to look at is because in the January 2020, this Nature Electronics journal, which is from a Nature publishing group, declared 5G is a technology of the year. So this is because near field communication is getting very focused, or it is getting important every day, and it is being done at two frequencies. One is 13.56 megahertz or 2.5 gigahertz, and that is a Bluetooth frequency. But both of these bands are hackable, and that's why people are trying to move to a new band which is compatible for this communication, as well as it should not be that much costlier. So the very famous example which we know is RFID tags. So this is your card, this is a tag, and there is a receiver, and it communicates, and then we do a lot of transactions and communications. So if you look at this, how the electronic circuit is there inside the tag, reader and a tag, it is like this. So the reader has a coil. There is similar kind of coil is there on the tag also. And a circuit consists of a diode and a resistor along with a one power source. So this diode is this is the one which makes the conversion of AC signal, which is coming from a reader, and converting into the DC, and that's why it is called as a rectifier. So what we have to read is the amplitude of DC voltage. So when we connect now a antenna for this communication in a series with a diode. This new component is called as rectenna. So this rectenna has been constructed several years ago, and of course it started with silicon. But people found it difficult to exceed the threshold cutoff frequency for it to a higher level. And that's why several new materials have been developed over the years, which are shown in this figure. So this F frequency shows the cutoff frequency in various bands like 4G, 5G, and 6G. And the new materials which were developed over the years in last less than a half a decade. So these are polymers, small organic molecules, then some oxides and carbon materials like CNT and graphene, and new generation of 2D materials. So CNT, carbon nanotube, have showed a tremendous potential almost a decade ago in 2010, and they showed cutoff frequencies in the range of 10⁻11 Hz. But over the years, they have been found very difficult and challenging to process them at large scale and get a similar kind of yield and performance from them. And that's why the attention came to oxide-based materials, and one of it is a zinc oxide. Because zinc oxide is a very famous material because of its various properties. It is even very famous in biomedical applications also because of antibacterial activities. But in electronic devices, this is because of its semiconducting nature and sufficiently wide band gap. So its combination with some other materials like indium gallium zinc oxide or pure zinc oxide has been used extensively in recent times in electronic applications. So they showed a cutoff frequency about 10-20 gigahertz. So this new generation 2D materials like WSC2, MOS2 recently only, they showed a potential where they can show the cutoff frequency about 10 gigahertz. So as many young researchers will be looking at this lecture, so I want to give some more basics in how to do the measurements for a DC and AC, AC and DC measurements for a diode. So what it requires is if you are fabricating micro devices, then you need a tool called a micro prober. So in which there are micro needles are there, and you connect it to your external power source like DC source, current meter, AC frequency generator, voltmeter, and oscilloscope. So when we perform this DC measurements and AC measurements, which are the parameters we have to look at are shown here. For DC measurements, we look at the current on-off ratio. So what is the current on-off ratio? Is this, so this is a diode characteristics. So the black line shows the characteristics in a linear scale of a y-axis, and this white line shows same graph in log scale. So this is off current and this is on current. So its ratio is important. The next one is ideality factor, is that how good your junction is formed. So its value is generally between 1 and 2. Then non-linearity. So in this voltage range, how much non-linear is your diode? And the responsivity is how quickly current is getting switched from low to high in a smaller voltage region. So the next, in AC measurements, we consider, as I told, AC component of a DC resistance, and it is called as impedance, and it is a complex quantity. Means it has a real part and imaginary part. So if we plot that impedance on a y-axis and the operating frequency on x-axis, then we will get two plots for a real part, which is black line here, and this white line is for imaginary part. If they cross each other at some particular frequency, then that is called as a intrinsic cutoff frequency. And in second part, if the DC output voltage, which is this one, if it is plotted as a function of frequency, then initially it is flat or it is not changing, and then at a particular frequency it starts dropping, and if its value drops below a 3 dB value, then that is called as an extrinsic cutoff frequency. So we'll see these two parameters in more detail for the work which I published. So to tell you a little bit more about the device geometry, you can see this is work published by UK researchers in 2015, where they made a Schottky diode between indium gallium zinc oxide and platinum as a metal electrode. So you can see it is a vertical transistor, the vertical diode, and this design is called as a sandwich design. So the top electrode is aluminum, then this is semiconducting IGZO, and platinum is the second electrode. So when the voltage is applied, the current flows in a when the voltages are applied, current flows in a vertical direction. So this is the DC characteristics, and it is plotted for different thicknesses of IGZO. So means by changing the thickness of semiconductor, we can change the device performance as it is shown here. So for thinner semiconductor, we will get large current and vice versa. So this is that impedance graph plotted as a function of frequency for various thicknesses. You can see for 50 nanometer film thickness, the cutoff frequency is around 8 gigahertz. But if the thickness goes to 100 nanometer, that cutoff frequency goes to 16.7 gigahertz. Means if you keep your electrodes far away from each other, then you get larger cutoff frequency, and that is the aim of getting that value larger and larger. And this is the plot for getting extrinsic cutoff frequency, and that is in between 1 to 2 gigahertz. So in January 2019, a group of researchers from MIT, USA, they published the very new idea of fabricating this Schottky diodes with this two-dimensional material MOS2, which has two polymorphs. One is a metallic and other one is semiconducting. So you can see this is a metallic part of MOS2, and it is noted here, indicated here as 1T, and 2H form of MOS2 is a semiconducting. So these are the two metal electrodes. One is a platinum, and other one is gold, and MOS2 is there in between. So you can notice what is the size of a junction here which is formed. So this is hardly a diamond width is hardly 1 nanometer. But if you see, look at the scale bar, then the separation between the two metal electrodes is between 1 to 2 micrometer. Means a junction of 1 nanometer is collecting a charge carriers over a distance of almost 1000 times larger than the junction. So they obtained a cutoff frequency in the range of 10 gigahertz. So making these kind of devices in a large scale is a bit challenging task. So by this time you have got idea that the device scaling needs various lithographic techniques, and these are listed here. So there are various techniques: UV photolithography, X-ray photolithography, electron beam lithography, ion beam lithography, imprint lithography, ice lithography, and there are various others. And these helps to get patterns starting from few micrometers to few nanometers. So in this our recent article, we have developed over the years a new particular lithography is called as molecular adhesion lithography. So to give you quick steps in this fabrication, so start with the substrate and pattern your one metal. So remember that we need here two metals, means with two different work functions to make a Schottky diode. So start with one metal one and you pattern it with photolithography, so on a substrate. Then dip this substrate in a chemical called as containing small molecules, and they are named as self-assembled molecule, SAM. So once you dip your substrate inside it, see these SAM molecules has one particular property that they stick to the surface of a metal and they get assembled in a vertical fashion. Please note that whether the surface of a metal is horizontal or this SAM molecule attaches only in 90-degree only. So once you take out the sample, you have a SAM molecule which is assembled only on metal one region, and it is not in the region on a substrate like a glass, and it is absent between the two metal electrodes. So in the next step, you deposit your metal 2 everywhere on the substrate. So I will show you here one small video to know what is the next step. So in the next step, apply a glue. So this is now your chip in which you are now applying a glue and let it dry for some time. And then take your tweezer and just peel off that top layer of a metal 2. So you can see you will end up with a substrate in which there is a metal 1, then that SAM molecule, and a metal 2 now which is left in between the two metal 1 layers. This is because this metal 2 is selected in a such a way that it has a very poor adhesion to this SAM molecule. And in the last step, now you expose this your chip to plasma, oxygen plasma. It will burn out all this organic layer and you will now have a chip with metal 1 and metal 2 separated by a nano gap which has a length equal to the length of this SAM molecule used. So here is an example of aluminum and gold metal electrode which are separated by this small nano channel or a gap electrode of a size of almost 12 nanometer. So there are various control parameters to obtain this, and they are listed here. So as I told you in one of the previous example, there is a sandwich structure in which the semiconductor is placed between two metals and it forms a capacitor like a geometry. So and that's why it has a large capacitance. But in this new structure which we saw just now, there is a substrate and a semiconductor, and two metals are parallel to each other, but in a lateral way, or on a chip they looks like this, and that's why they have very low small capacitance compared to this structure. And because of this low capacitance, there is a possibility that these devices will operate at higher frequency. So in the next step, we take that chip which has gap electrodes and spin coat our semiconductor on the top of it by using an ink of zinc oxide, and then we heat it at some temperature to evaporate the solvent, and this is a high resolution TEM image, shows this aluminum electrode and gold electrode, and this zinc oxide material is filling that nano channel. So note that aluminum has a work function of 4.3 electron volt and gold 5.2 electron volt, while the zinc oxide, semiconducting zinc oxide, has a work function of 5 electron volt. So these are the chips which we fabricated on a 2-inch and 4-inch wafer with hundreds and thousands of devices on it. So I would like to now discuss the geometry of this structure, and this is you can see the circular portion inside is a gold, and it's surrounded along its perimeter with this second metal electrode. And if you see, the gap is between the two all around its perimeter, and we call that as a scaling parameter W. So we will now change the value of W and we'll look at the device performance. So this is the Tcat simulation which shows how actually the diode works. So in the case, the example of MOS2, I mentioned you that the two metals are separated by almost 1000 times, or they are separated at a distance of 1000 times than where the junction is. So but in this our device, you can see this red line shows the Schottky barrier height boundary or the junction, which is separated by less than 20 nanometers, and that's why the charge collection will be very quick. So these devices were measured for AC, and the measurement is called as S parameter measurements. So these S parameters were first simulated using the Tcat, and when we collect the data for port 1 S11 is this one. So this is the input wave and the reflected wave, and this data is called as here S11. And when we plot it here, you can see this black line, which is at zero bias. This line is completely flat, and it is even flat even at 100 gigahertz. So this tells us that the device is having very low parasitic capacitance, and its capacitance and this is it has a value of 0.34 picofarad, and it is very flat up to 10 raised to 12 hertz frequency. And from this data, when impedance is obtained in a real and imaginary part, as you can see, it tells us that these devices have potential to show cutoff frequency of 0.8 terahertz. So now this is the experimental data, DC. So we will start with the DC. So these are the IV characteristics for a forward bias for different widths. So this is 250, 500, and the largest was 500 micrometer. And when this data is plotted in log scale, you see this is a reverse bias current, which is of the order of 0.1 nanoampere, and this is the on current, which is 0.1 milliampere. So here we use the two different types of zinc oxide. One is intrinsic zinc oxide, which is shown here in a violet region, and aluminum doped zinc oxide, which is here in the blue color. So this is because because both forms of zinc oxides are well-known materials, but it has one particular reason which I will tell you in the next slide. So this rectification ratio is plotted as a function of bias voltage, and of course this zinc oxide shows a little bit large rectification ratio, but both of the devices show rectification ratio above 10⁵, with and that is important. So the responsivity and its unit is ampere per watt, and it is maximum close to zero bias, and its value is around 11. So this value of 11 is very high compared to silicon diodes, and its thermodynamical limit is actually 19. So there are not many diodes which can show this kind of responsivity. Or in the previous case of that MOS2 example, the responsivity was of the order of 6 or 7. So now we look at the non-linearity. Then for industrial applications, this non-linearity has to be above 3. So, and it is obtained by this equation here, is just the ratio of conductance and resistance. For both the diodes, for both the materials, zinc oxide and aluminum zinc oxide, you can see this non-linearity is 3 for all the voltage region. So for this diode, we obtained a Schottky plot in which 1/c square capacitance is plotted as a function of voltage for ZNO and AZNO. We notice that there are two dips are there in that plot, and this is related to shallow and deep traps. So these traps are shown here by various symbols. So this red one are the deep, and small one are shallow traps. So in 1960s, there was a lot of study, theoretical study on this, and there was a prediction that if there are more number of deep states are there or less number of shallow states, then the wave propagation through that device will be faster. So here, by adding the small amount of aluminum, we have decreased the shallow traps and increased the deep traps, and you will see now how they got benefited. So the series resistance of a diode was obtained by Cheng's plot, and it is of the order of 230 kilohertz, which is one order small than its highest resistance at the maximum voltage. To give you a small introduction about again to obtain its extrinsic frequency. So this is circuit needs to be built in which this is the diode, and it is connected to a function generator or frequency generator through a small circuit called a bias T, and its DC output voltage is measured across a load resistor here. So this is the performance of extrinsic cutoff frequency, DC output voltage as a function frequency for 5 millimeter and 500 micrometer diodes. You can see 5 millimeter diode has a cutoff frequency of 3.6 gigahertz, and it increased to 5.7 gigahertz for 500 micrometer diode. And this cutoff frequency, of course, all the parameters like DC output voltage, cutoff frequency, everything has a reverse relation. Means smaller the diode, larger is the cutoff frequency, but it will give lower DC output voltage. So in this slide, it summarizes intrinsic cutoff frequency performance of both ZNO and AL-ZNO diodes, and at various scaling. So I will just discuss this middle part graph where it shows aluminum zinc oxide semiconductor with 5 mm, 1 mm, and 500 micrometer width of a diode. So you can see as the width is decreasing, the cutoff frequency has gone up from 6.6 gigahertz to 300 gigahertz. So this is one of the highest cutoff frequency reported uh, except 3.5 semiconducting materials. So this is because the capacitance of the junction capacitance of the device is very stable uh, up, up to 10 gigahertz, because this is the limit of measurement, and it has been found very flat. So corresponding to that, the tan delta is a loss also found to be very minimal, and that's why the diodes have been seen to work at higher cutoff frequency. We have measured indium gallium zinc oxide diodes also, and they also show intrinsic cutoff frequency of 100 gigahertz and extrinsic cutoff frequency up to 8-9 gigahertz. So this lithography is very versatile, and it can make these patterns not only on a solid substrate but on a flexible substrate also, and we can make directly rectifier circuits like full wave rectifier circuits also on the chip. So this is my last slide, in which because my title talk was quite general and it was about RF devices. Here in this slide, I want to talk about another component of a circuit called the inductor. So a few years ago, researchers from University of California, Santa Barbara, demonstrated this proof of the concept in which they used graphene to make inductors. So this was not just pure graphene, but it was a doped graphene or intercalated graphene. So these are the layers of a graphene black spheres, and they were intercalated to make it highly doping. So they compared the performance of the inductor. So this is a coil is an inductor, and they measured the RF performance of it. So they plotted inductance as a function of frequency, and they compared this graphene inductor with existing state-of-the-art copper inductors, and they noticed that the inductance is quite high. So even if you see the numbers are small, they're like 1.5 nanohenry to 1.7, 1.8 nanohenry. This is a significant improvement. And so they saw the scaling of the same with thickness of graphene and copper. So you see this black line is the for copper inductor, and it stops showing better performance when the thickness of copper goes to 200 nanometer. But graphene, as we know, we can make it even a monolayer, which is a 0.1 nanometer, 0.14 nanometer thick, and still it can show better and better inductance at that frequency. So with that, I will summarize that nanoelectronic devices are still a lot of development can be possible, especially in RF and bendable circuits. So the way forward is to make new designs and increase the accuracy of measurement. To make these devices, new lithographic techniques can be used, already existing one or new can be developed. So all these efforts are just to go beyond the routine material synthesis and basic characterization, and really making use of the materials. Thank you.
Yeah. Thanks, Abhay, for this wonderful presentation. And it is really fascinating to see that such a simple method to make these nano devices and which can work in such a high frequency range. And you have really explained well about the basics, and I hope that it will help the researchers who are working in this field. And I have several
Thank you.
queries regarding this work. So I'll start
Sure,
asking
sure.
questions. So first question of mine is that what is the meaning of the scaling of these electronic devices and how it is relevant for this
Right.
RF electronics?
Yes. The scaling is basically about how we can change its dimensions. So, and what is the change in the performance of the device? So, for example, here, various dimensions, when we talk about material, we have thickness, width, and length. So, if you change any one of it, then that can be called as a scaling. So, for example, in the diode structure, we changed the total width of a diode, and in this inductor, you can see the thickness of the material is changed. So, if you change the thickness from smaller to larger, then in which direction you are getting the higher performance is the indication to go forward. So while here in this case, you can see the width is decreased, then the cutoff frequency has gone up. So this is because if the device dimension is small, then the propagation of the input wave is faster towards its output port. And this is what everything scaling is about. And this is a little bit different than the scaling what we know about field effect transistor, where we look at the one parameter, not the footprint of the diode transistor, but only the gate length or the channel length of a transistor.
Okay. So my second question is, so which properties of the materials important for these RF electronic devices?
Yes, so this is a very important question because not any material can be used it in RF. So in general, when we talk about materials, so they are actually only materials. But when we talk about this electronic devices, we have to call them as electronic materials. So this electronic material, so this is a very old concept, but it is not widespreadly used. So these electronic materials are the materials which has less amount of impurities and defects. So any material which has this property should be actually called as the electronic material. So that was the efforts in this our study to make this zinc oxide less defective, but by adding it's even a small amount of impurity. So by doing that, we have controlled its conductivity, and that's why it changes its permittivity. So the permittivity, conductivity, and the mobility of a charge carrier. So these are the basic properties of the material needs to be understood well before starting these RF applications.
Okay. So my third question is, how did you make this setup for this measuring this such a high cutoff frequency or the extrinsic
Yes.
cutoff frequencies?
Yes, so this was actually very time-consuming process for us. Here, as you can see, um, when we make electrical setup, which I showed it you previous in the probe station, so these are very well for DC measurements. But when it comes to AC, lot of factors needs to be considered. One of it is called as a signal to noise ratio. So means it has to be higher, or the noise in uh, the signal has to be reduced, and that is done by using a process called as impedance matching. So this is a very important section of making the RF circuits called the impedance matching. So means what it means is that when the RF wave is going in forward and in the backward direction, the impedance should be matched. So this impedance matching from industrial perspective, its value is actually 50 ohms. So all this your setup needs to be calibrated for 50 ohm resistance, so that now you can compare your all the measurements coming out of it. To make that setup, the calibration was done multiple times, and this value of load resistance was calculated by this impedance matching, and then only we can get actually the maximum output voltage if the matching is proper. And to do this, if you are not an electrical engineer, then it may take from 6 months to 1 year of time.
Oh, it's
Yeah,
it's really take
yeah.
time.
Yes,
And
it is just to make the setup. Yeah.
yes. So, and my fourth question is that it may be a little repetitive. So, why do your devices work at this such high frequency? What do you
Yes.
think?
So actually, yeah. So coming to this slide, this the geometry of the electrodes which we have ended up with from this molecular addition lithography is actually, it is the intrinsic property of those electrode design itself. So here you put any material, we are expecting that you will end up with higher cutoff frequency, and this is because of very small parasitic capacitances and high current density. So here in this uh, device simulation, as I showed, as soon as the charge carrier crosses the junction, it is captured, and that's why we can have high current density. But the thickness of these metals are hardly 40 nanometers. So even if you are seeing these are the parallel metals separating a semiconductor, these are actually just 40 nanometers. So that's why the parasitic capacitance is low. And this is what makes this whole geometry supportive for the high frequency.
Okay, thank you. And my next question is that what can be the potential applications of this high frequency diode, such a high frequency diodes?
Yes, so to starting with, so these are very special kind of diodes, and it is only used for RF devices. So when I talking about here transmitters and receivers, as in I showed it in the previous slide, for communication we need the transmitters and receivers, and where if you put a diode, then only you will get a rectification and control of the voltages. So similarly, there are other kind of circuits are there for RF. They are called as frequency doublers. So as you know, in radio we have AM, FM on other bands. So like this, various bands needs to be created for RF communication. And that's why this frequency multipliers or doublers needs to be made. So other part is actually called as a mixer. So this is the reverse of the frequency multipliers. So this is just like mixing the waves. So everywhere, if your diode is not responding to the frequency, then making these devices will be difficult.
Okay. So our next question is that what are the future studies what you can take up, what you are going to take up on this work?
Yes, so there are so few small tricks are left to be tried out in making this device diode structure or the electrode structure, in which there have been frequent inquiry by the researchers, basically from physicists who understand the dimensions a little bit better. It's like if you now take a channel length which is of the order of below 5 nanometers, then you enter into a quantum tunneling region. So now the question is whether these devices will work in that region or not. So the best before doing that, these devices needs to be simulated first, or to understand whether it works at this tunneling region or not.
Okay.
And then if you have to reduce this capacitance little bit further, take these electrodes little bit farther than 20 nanometer, let's say 25 nanometer, and then we can see that where the performances goes up. And apart from that, new materials, as I just told you, 2D materials with and without doping can be used as semiconductors.
Okay. Yeah, thanks. So coming to the last question. So as you have worked in several foreign institutes and the research institutes, so I want to ask that what are the main differences in the research infrastructure and as well as research environment between the Indian institutes and also the institutes as you have worked in the UK and Germany. So what can you comment on that?
Yes, actually, famous question from young researchers um, who are trying to climb up the ladder. So basically, we have a very wide band of institutions here in India, starting from small colleges to private institutions to universities, government universities, and then we have uh, special ICER kind of institutes, then IITs, and then each funding agency like DA, DST has their own special institutes. So we have actually quite complex structure, and all of them are done in a such in order to achieve some particular goal. So our structure has its own advantage, but in what I observed in out, outside of India, like especially in Germany and UK, they have little bit different pattern. The most important difference is that they have in last 20-25 years, they have created a new group of institutes which are in between industry and academia. So there are huge number of these institutes are there, which communicate between the academics like university researchers and industry to bring them together and understand the basics of physics, and I use it for the applications. And this is a very key idea which they developed, and they are being successful. So now when you are writing now the for the funding proposals, there you can, if you are academic people, when they want to now the research proposal, they find it very difficult to communicate with industry, or the industry people even don't know actually what academics people are doing. So that's why these R&D centers are playing very important role there. And that's why the job openings have now been multifold, means because they have now academic sector, hybrid sector, and industry, and there are job openings in all the bands. And here, actually, that middle band is missing from India.
Okay. So, so you think that means we have to improve in that
Yes,
direction?
so if like the researchers like you, or like for that matter me also, we should pay attention to actually making this, or even we all the time we should ask our peers and our seniors to come up with some ideas to start these kinds of consortiums uh, called a hybrid structure and communicate between industry. and academia.
Okay.
Yeah.
So that's it. So thanks, Abhay, for this wonderful discussion today, and it was really nice to have you with us.
Yes, thank you, Suman. Uh, Hope you will get fantastic speakers. Of course, I will also follow this channel now
Yes.
to see. Yes, actually, we most of the time keep reading the papers and all that, but we hardly get a chance to meet the people who really did the research.
Yes.
So, hope this platform will give this opportunity to for all of us.
Yeah. Thank you. We will also carry on in this direction. So to our viewers, if you have any queries about this Dr. Abhay's work, so you can directly contact him to his email ID. And I hope this session has helped you guys to understand the basic things and towards this subject. And as Abhay said, in future, many other prominent researchers will be joining us here. And please comment and give your suggestions so that we can improve further. And that's it for today. And thank you, Abhay, and bye.
Okay, see you. Bye.
Bye, guys.
Bye.